Hello, my name is Scott Grizzard. I'm from the University of South Florida. This is Calculus 1. Tonight what we're going to be doing is the basic derivative rules and the power rule. So you can't use the power rule or the other derivative rules on the test, but if you understand how the proofs work, there's a question or two that understanding these proofs will help you kind of understand what else is going on. So that's what we're going to talk about tonight is the basic derivative rules. Okay, so the one that, of course, is very famous is the power rule. So let's start there. So what I have on the power rule, let's state what it is. So the power rule basically says, and I'll state it in its most general terms. We're not going to prove it in its most general terms tonight, but we can, and it's a theorem, but we can state it in its most general terms, and then we'll prove it in its most general terms later. We need a couple more tools. Today, what we're going to do is prove it for positive integers. So the power rule in general, to be proved, in full power later, in full glory later, is as follows. Here's the statement. Let C be a real constant. Okay? Great. Thank you. Person who told me that I was doing it wrong. Yes, I was intending to have the screen behind me. I don't know why I didn't think to put it back. Okay, so the power rule in general to be proved in all of its glory later. Let C be a real constant. Okay. Then d over dx of x to the c. Now this is important. The constant is in the thing that moves is the base, not the constant. Then the derivative of x to the c equals, exists whenever, I should say wherever, cx to c minus 1 is defined and finite, and d over dx of x c x to the c equals cx to the c minus 1. And I could have, if c is a real constant and if cx to the c minus 1 is, I can rewrite this a couple of ways to make it a little bit clearer. But the big point is this thing right here. The derivative of x to the c equals cx to the c minus 1. And we've already seen this a couple times, right? Example. All right, so we've already done this a couple times, right? So we already did the limit as, we already did f examples. If f of x equals x squared, then f prime of x equals 2x. So we've already seen this, right? So f prime of x equals the limit as h goes to 0 of as h goes to 0 of f of x plus h minus f of x all over h, which equals the limit as h goes to 0 of, I just put in x squared here, so x plus h squared minus x squared over h equals, now I just do the thing, so it's 2x plus, I'm sorry, not 2x, x squared plus 2xh plus h squared minus x squared. My brain is going faster than my pen. Don't forget the limit sign, h. And then things cancel. I factor out the h. So I get h over 2x plus h all over h. The h's cancel. And I wind up with the limit as h goes to 0 of 2x plus h sub n 2x plus 0 equals 2x. All right. So that's true. But I can also do other things. So we've done this one in class too. So last time, we did one of these already. So if you remember from last time where we did that marginal cost thing. So last time we did one where this was the limit we were doing. So last time, oops, I'm still clicking on the wrong thing. We did this. Right? So we had, last time we had, this was c of q equals the cube root of q. And we used the difference of cube thing, and we wound up with 1 over 3 to the q to the 2/3. Well, remember that c of q equals q to the 1/3. So this right here from last time is actually 1/3 q to the negative 2/3. So if we had applied the power rule, right, to do d over dx of q to the 1 over 3, we would have taken the 1/3 and pulled it down and then subtracted by 1. So if we had the power rule, we would do 1/3 q to the 1/3 minus 1, which equals 1/3 q to the negative 2 over 3. Which, you know, would have made our lives a little happy. Okay? So how do we feel about this 1 to 5? Okay. All right. Of course, I can't use that on the test, but, you know, I could have. Not could have used it on the test. But if I had access to this power rule, I could have used that, and that would have been a much shorter thing than all of this. Again, this right here would have been much shorter here, right? Because with the power rule, with rule, d over dx of x squared would equal 2x to the 2 minus 1 equals 2x to the 1, which equals 2x. Okay. So this is very, it's the first one. It's the one that everybody goes, oh, yeah, I know how to do calculus because I know the power rule. Okay, well, there's more to it than that, but okay. So it's kind of just a really nice little tool to have in the belt. So what we're going to do today, we can't prove it, as I said, we can't prove it for any C. But what we're going to do today is prove part of it. Okay? We're going to prove that it works for any positive integer. And the way that this happens, there's something called, let's see here, what am I trying to do here? So what I'm basically going to try to do is, over the course of this period of time, we're going to bootstrap the power rule. So there's an exercise in your book. Once you have the power rule for positive integers, there's an exercise in your book that once you have the derivative of 1 over x in your disposal, you can actually prove you can actually prove the power rule for negative integers. So it takes and then once you have that, later you prove it for rational functions. So it's a pretty powerful tool. Notice also here that you can't use it when q equals 0 because the derivative doesn't exist. That function doesn't exist there. So let's kind of state what we're going to do right now. So where are we? What we're going to do is a small thing. We're going to do the power rule for positive integers. Okay, so tonight we're going to prove the following. Okay. If n is a positive integer, then d over dx of x to the n equals nx to the n minus 1. All right, so are there any questions? Okay, so we want it to work for squares, cubes, and all sorts of things like that. Okay. Well, let's look at what would happen here. If I was doing it for cubes, right? And this was actually a quiz question. So if I was doing it for cubes, I would do something like this, right? So for cubes, it would be something like this. Right? So f of x equals x cubed. So f prime of x equals the limit as h goes to 0. That looks like a horrible h. Excuse me. Got stuff all over my desk. Okay. The limit as h goes to 0 of f of x plus h minus f of x all over h, if I was just doing the cubes, would equal the limit as h goes to 0 of x plus h cubed minus x cubed all over h equals the limit as h goes to 0. And what I'm going to do is I'm going to expand this. So trust me when I say, verify on your own if you want to, that this thing right here, stop that, equals 3x cubed minus, I'm sorry, not 3x cubed. Don't trust me. X cubed minus 3x squared h plus, don't trust me at all, 3xh squared plus h cubed minus x cubed over h. So this stuff here, this stuff here came from there. And this stuff here, that came from that. Okay. So these two terms are going to cancel. And notice that I've gotten rid of everything without an h in it. So now I can factor out that h on the top, and I get h times the quantity 3x squared plus 3xh plus h squared all over h. The h's are now going to cancel. And what I'm left with is the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And that, as h goes to 0, becomes 3x squared plus 3x times 0 plus 0 squared, which equals 3x squared. How do we feel about that one, 1 to 5? So that was kind of, and I asked that on the quiz. Usually I do the lecture right after the quiz, because there's kind of a process that goes in here, isn't there? I cancel the thing, the thing in front is going to cancel with the thing in the rear. Okay? And then everything will have an h in it. So I factor out the h. And when I take only one term survives when I do this. Okay? And the same thing happened here. When I got the 2x, stop that. The x squareds canceled, and everything that was left had an h in it. And then the only term that survived was that lead term with only the 1h. Because I factored out the 1h, then it went away, and I was left with something that when it went to 0, there was only one term left. All the other things had zeros in them. So how do we feel about that? 1 to 5. I'm not really getting a lot of 1 to 5. Oh, everyone's in Discord chat. Very nice. Okay. Well, that's kind of cool. What I want to do is I want to do this in general. So, I mean, I could do the fourth. But when I do the fourth, according to the binomial theorem, there's going to be a term here that's x to the fourth. And then there's going to be a term here with an x cubed that will hang out with some number in the front. So if I want to really prove this, I need I'm going to need a theorem, right? So let's grab our theorem. I'm going to need that binomial theorem in order to prove this in general. So let's grab that old binomial theorem and stick it right there in front of us. Let's stick the old binomial theorem in there. I'm going to need this. This, by the way, where it says theorem 0.312, that's from the notes for this section. Okay. So let's do it. Okay, so proof. I should do proof in red, shouldn't I? It should look nice and bold. Proof. It should be in blood. There we go. Proof. All right. My strategy is good. So I want to show f of x equals x to the n. I want to show that the limit... as h goes to 0 of x plus h to the n minus x to the n all over h equals n x to the n minus 1. And my strategy is going to be as follows. Use h definition of the derivative. Expand x plus h to the n using binomial. Binomial, which I cannot spell. Theorem. Okay. Expand x plus h to the n using the binomial theorem. Cancel the x to the n's. Factor out the h from everything else. Then cancel the h. The only surviving sub in the 0, and the only surviving term is n x to the n minus 1. Okay. So that's how we're going to do it. How do we feel about this strategy 1 to 5? That's basically what I said we would do. We kind of have this intuition about what's going on, right? There's going to be one term that survives after just like in x cubed. There was one term that survived in x squared. There's only going to be one term that survives. And our supposition is that there's only going to be one term surviving. Period. Right. So the question again, this is not on the test, but as I said, understanding the proof, not understanding the proof in that sense, but understanding these kind of more abstract substitutions will help you on the test. So the proof is again not on the test, and you can't use the power rule on the test. But for one question in particular, having a little bit more practice at this and kind of understanding what's going on is very, very helpful, if that makes sense. So I don't want to so I don't want you, if you're having trouble with limit computations, those are certainly more important. But if you're trying to move from a C to a B or something like that, this is probably not the most efficient use of your next hour. But if you're trying to move from a B to an A or improve your A and be ready for the understanding of the next thing, this may be something you want to see. You need to see it before that, it's useful to see before the test. I'm talking too much. It's useful to see before the test, but not to necessarily have it memorized. Okay. So that was way too long. My TA needs to bonk me on the head when I do that. If you could figure out a way to remotely do that, I'd appreciate it. Now, okay, so this was the binomial theorem. This is what we're going to use to do it. Okay, so f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay. Now, our f is x to the n. So we've got the limit as h goes to 0 of x plus h to the n minus x to the n all over h. Now, I'm going to try to keep the binomial theorem on the same page, the same screen here, because I'm going to use the binomial theorem right here. Now, into 0, x to the n, h to the 0, plus n choose 1, x to the n minus 1, h to the 0, h to the 1, plus n choose 2, x to the n minus 2, h to the 2, plus dot, 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 all the stuff in the middle. Pattern continues to n choose n, x to the 0, h to the n. And then I need to remember to carry this negative x to the n, minus x to the n. So this bit here is still here at the end. All over h. There's my expansion. Now, I claim that I need exactly two of these I need exactly two of these items. Okay. So what is n choose 0? What does that mean? What does it mean? What is n choose k? A little aside of combinatorics. So n choose k is defined as the number of ways to choose k things from an n-sized set where order does not matter. So, if I have 52 cards in a deck of cards, okay? I've got my Margaritaville deck of cards. These are very important because, the whole, margarita you can never reach. So these are my calculus cards. Now, I take my 52 cards. All right. How many ways are there for me to choose one of the 52 cards? Well, let's see. How many choices can I make? I could pick this one. I could pick this one. I could pick this one, right? So how many different cards can I pick if I only wanted one card? How many different ways are there to pick just one card? Yeah, 52, right? There's 52 ways to pick one card. So, in general, n choose 1 equals n. How do we feel about that, 1 to 5? If I've got n things, right, and that's a positive integer, if I've got n things, there's n ways to pick one. There's n ways to pick one item. Okay. Now, how many ways are there to pick? If I've got 52 cards, how many ways are there to pick 51? This is a little bit trickier, right? I want to pick 51 cards. But I could also think, how many ways are there to leave one card left? Right? Because I'm taking 51 cards from this deck. Every time I do that, I leave one card. So how many options are there to leave the one card? How many ways can I leave one card behind when I deal the 51 cards from the deck? Right? There's 52. There's 52 options for the one card I leave behind. No. So I'm dealing 52 cards. I'm dealing 51 cards. Right? From 52 cards. So how many ways are there for me to deal 51 cards from the 52 cards? I may be mistaking the question because I'm getting a lot of 51s. Right? Well, that's the same question. If I give someone 51 cards, I've chosen to leave one behind. So there are 52 ways for me to choose to leave one behind, which is has to be exactly the number of ways there are to deal 51 cards from the 52 card deck, right? Because all you do is pick the one that's left behind, and I could give you one card and keep 51. But that would be the exact same thing as you giving me 51 cards and keeping one, right? If I pick the 51 cards that I get, the card that you get is the only option. So there's only 52 ways for me to do this. So we have that n choose n minus 1 equals n. Now, how many ways are there for me to give you all the cards? There's only one, right? I give you all the cards. Now, if I give you all the cards, how many cards do I get? I get no cards. So, how many ways are there for me to get no cards of the 52 cards? How many ways can I get no cards? One. All right? There's only one way I get no cards. I gave them all to you. How do we feel about that, 1 to 5? That's kind of a cool thing when you think about it. So now let's go back to our theorem, right? I know that I know that my head's in the front here. I've got a big head. Let's get rid of my head. Okay, well, that's good. Let's try that again. Right? We'll delete all this. So, what I'm going to do is all I'm going to do is I'm going to take this term here and I'm going to sub in for these things, right? So the only thing I'm changing is n choose 0 to 1 and n choose 1 to n. And I'm leaving everything else the same. 1 to 5, how do we feel about that? Okay. All right. Okay. So now what? The question is, what do I do now? Well, look what's going to happen here. First of all, this term just became x to the n, and there's an x to the n here. Those two terms cancel. Just like we thought they would. And now I'm left, and everything that remains has an h in it. I'm going to factor out one h from every term. Okay? So I'm going to have h times. Now, this first h, I only have one of them. Nx to the n minus 1. The second term has two h's. I'm going to take one. Stop it. The second term has two h's. I'm going to take one. The third term is going to have three h's. I'm going to take one. The fourth term will have four h's. I'm going to take one. And so on and so on and so forth. The nth term has n h's. I'm going to take one. The h's cancel. What's left is the limit as h goes to 0 of nx to the n minus 1 plus n choose 2 x to the n minus 2 h to the first plus dot 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 plus n choose n x to the 0. Yeah, I know that's 1, but I don't want to. If I simplified this term, I'd have to add another term in here to make the dot 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 work, and I don't want to. So I'm just going to leave it. H to the n minus 1. Now, every term has an h in it. Right? And this is a polynomial in terms of h. Because I don't want to write the new pattern in. It's annoying. Oops. He went away. Okay. Every term has an h in it now, except one. So I'm going to directly sub in, and I'm going to wind up with nx to the n minus 1 plus n choose 2 x to the n minus 2 times 0 to the first plus dot 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 everything, right? This term here has a 0 squared. This term here has a 0 cubed. This last term here has a 0 to the n minus 1. And 0 times anything is 0. Okay? It's not erasing. How do we feel about that proof? 1 to 5. Okay. So the key here is that everything in the middle cancels. And it makes us happy. Everything that's left will cancel. So the 2x's cancel. The x to the n's cancel at the end. I factor out an h. They cancel. And every term except that lead term has a 0 in it when I'm done. It's a nice little proof. Okay. Let's do another little thing. That's the power rule. Now, I'd really like to be able to take derivatives of polynomials, right? So remember, I could take limits of polynomials very quickly with this direct substitution thing. Wouldn't it be nice if there was a quick and easy way to deal with polynomials? So what did I need? In order to do it for limits, I needed a constant multiple rule. So what were the laws? What were the limit laws I had to get at for in order to do this for polynomials? I needed the following, right? I needed a constant so I needed a power law, right? I needed a constant multiple law. I needed a constant law, or the limit of a constant. And what else did I need? I needed limit of a constant, a power law, a constant multiple law. Oh, and I needed a way to deal with sums. So I needed a sum law. Okay. So let's see. I now have a way of dealing with powers. I need a way to deal with constants, sums, and constant multiples. How do we feel about that? 1 to 5. What I need in order to deal with polynomials. Okay. Well, this is on the bootleg. All right. This we just did. So let's go after one of these other ones. Okay. So I want to make a small distinction, and I'm going to mention this again. I've already mentioned it once, between a constant as a function and constant as a number. Right now, I'm going to deal with constant as a number. Okay. So right now, we're going to deal with constant as a number in order to do the constant multiple law. I want to deal with this carefully after the test. I don't think I'm going to get to it today, and I probably don't even want to, because it's a little bit confusing, and I don't. You have to kind of sit and think about it for a moment, and then once you get it, you're fine, and then you go back to doing whatever. But let's do this constant multiple law here. All right, we would like theorem. It's more of a lemma. The constant multiple rule. All right. And so what does it say? Let C be a real constant. Okay. And f differentiable at x. The constant multiple law says the following. Then d over dx of c times f of x equals c times d over dx. And it looks just like the limit law, right? It looks really similar, right? I pull out the c and I'm good. Which is what the limit law did. Well, let's prove this, and the proof is relatively straightforward. We'll use the limit law. Okay, proof. What is it I want to show? I want to show, by the time I'm done writing the want to show, it's obvious how you do it, right? I want to show that the limit as h goes to 0 of this thing right here. So remember that cf of x plus h is going to be what? C times f of x plus h minus c times f of x all over h equals c times the limit as h goes to 0 of f of x plus h minus f of x all over h. Wait a minute. Strategy. Use the constant factor and use the constant multiple law. I mean, why am I writing this again? It's obvious now what's going to happen, right? I'm going to pull the c out. It's going to show up here. I'm going to apply the constant multiple law across the limit, and I'm going to be done. All right. The key to this proof is that you have to know that this right here is d over dx of c f of x. That's the definition of d over dx of c f of x. And this right here is the definition of d over dx of f of x. So the notation is harder than the thing you're trying to show. 1 to 5, how do we feel about that? The notation is actually the harder part of the problem, right? You have to know that you have to be comfortable with this idea. D over dx of f of x equals f prime of x. You have to be comfortable with that idea. I think this is lousy notation. I think the bracket should be here because you're taking the derivative of f and then going to x. But no. Technical reason that nobody wants to listen to because I'm the only one, apparently. There's a lot of things that I do that I'm not the only one. This is one of them. Okay. Strategy. Factor and limit law. You know, it's like a duh. Okay, let's just do it. Because, you know, what else are we going to do? On a Thursday evening, you know, we could go eat dinner or study for the test or, you know, do something else. So the derivative of this equals the limit as h goes to 0 of cf x plus h minus cf of x all over h equals, let's factor it a little bit, limit as h goes to 0 of c times the quantity f of x plus h minus f of x all over h equals, well, constant multiple law, c times the limit as h goes to 0 of f of x plus h minus f of x all over h equals c times d over dx of f of x. How do we feel about that proof, 1 to 5? That doesn't even deserve a QED, right? It's just a... So the important thing is I have to know what I'm matching. You want this thing right here, which is the same thing as f prime of x, to be on the right, with the c outside of it. Okay. So example of using this, right? Example. D over dx of 3x squared equals 3 times d over dx of x squared. That would be the constant multiple law, right? And now we've got, oh, well, now I can deal with the x squared. I've got 3 times 2 times x to the 2 minus 1, which equals 6x. This is the power rule. Okay. So now I can deal with, terms with one term. All right, well, let's deal with constant functions. I will get to that. Any questions, by the way? No? Okay. Well, for the sake of argument, let's deal with the constant law. So, constant as a number versus constant as a function. What does a constant function look like? I'm going to write notation right now that I never want to see again. Especially, I don't ever want to see you write this notation. Okay, the example was I just took 3x squared, I applied the constant multiple law to pull out the constant, and then I used the power rule to do that. Okay? All right, so constant as a function. So if I have a function that's a constant, what does it look like? So if I have the function, what is the function constant as a function? So what does the function okay? Remember that a function is nothing but a set. So f is actually, right? F as a set, not f of x equals 2. If I have 1 and I plug it into this function, what's the y value going to be? It's going to be 2. If I have 0, I'm going to get back 2. So the point is that this is actually a set. This is the set x2 for all x in R. How do we feel about that? 1 to 5. That this thing, f of x equals 2, is actually a function. It's a set. Okay? It's a whole kit and caboodle set. 1 to 5. How do we feel about that? So when I do that, and what kind of set is it? It's a line. Right? F is a line. So it's not 2 as a number. It's the set that gives me that always has a y value of 2. All right? And that's a subtle distinction, but it can land you in trouble if you start thinking about things as numbers. You have to think about what's moving and what's not. Okay? The point is that the y value doesn't change. So the change should be what? It should be 0. But it's important to remember that this is a set. So I'm going to define this. Constant n equals the set xn for all x in R. Okay? It's a fixed n. So this is going to be the constant function here. All right? So when I take the derivative of it, I'm going to get back the 0 function. So d over dx, because I've got no change, right? Of constant n equals the 0 function. Okay? It's not that the derivative of a constant equals 0. The derivative of a constant function equals the 0 function. Okay? Because if what's the change in x over y if I didn't change? So that's the important thing here. What is the change in x? Sorry, what is the change in y over the change in x if y never changes? Right? How do we feel about that 1 to 5? So I want to be careful about using this proof as a rule. Okay? I'm not but the derivative itself is not 0 as a number. It's 0 as a whole function. It's this whole line. But that's important because if I ask the question, what is f prime of 3? Right? If I ask the question, what is the derivative at x equals 3? That is a different question than asking what is the derivative of f of 3. Well, what do you mean? F of 3 is the number, the output of f, the y value? Or do you mean the derivative of the function around 3? Or at 3, right? The derivative of the function at x equals 3. And it's a very easy thing to get confused. And I probably made it worse for like half of you and better for the other half. Okay? So I just want you to, and I never want to see this again in your thing. Okay? For as long as you're concerned, this is right here. Let n be a real number. The d over dx of constant n of x equals the limit as h goes to 0 of constant n of x plus h minus constant n of x all over h, which equals the limit as h goes to 0, this right here and this right here, right? This right here, constant n plus h, is going to be, well, n, by the definition of the constant function. The constant function n minus x is going to be, let me think about it for a moment, n. And I'm going to go all over h. But n minus n equals what? Okay? So what I'm doing this whole time is when I take the derivative, I'm taking the derivative of a flat line. Okay? But it's important to know that when I take the derivative of a line, I get back a line, the 0 line, as a function. Now, at any particular x, d over dx of constant n of x equals 0 as a number, right? For any fixed x, the derivative is 0. The slope of the tangent line is 0. But there's this kind of subtle little distinction that you just have to, I don't even want it in the front of your head. I just want it kind of in the back there itching. Wait a minute. Am I talking about taking the derivative of the constant function, or am I talking about taking the derivative at a particular constant? Because those are two different questions. Okay, I just want this in the back of your head. Of a constant function, or am I taking the derivative of a function at some x fixed and constant x. Okay, so is everybody okay with this? 1 to 5, how do we feel about this? Again, I don't want to confuse you, but I just want it in kind of the back of your mind, kind of itching sometimes. Just make sure that you know what you're taking the derivative of, right? Am I taking the derivative of a flat line, right? If I'm taking the derivative of a flat line, okay, I'm going to get, so if f of x equals 4, if y equals 4, right, that's what I'm going to get. Oops, you can't see that. If y equals 4 and I'm taking the derivative of that function, what's going to be left? What's the change in y? Well, 0. Right? So I'm never changing y. Therefore, what I'm going to get left is a flat line back. But that flat line back is going to be the line 0. It never changes. For any x, the derivative of this is 0 as a number. For any fixed x, it's 0 as a number. But if I'm thinking about the derivative of the function as a function, that derivative is the 0 function, right? The constant function 0. So in other words, just keep it in the back of your head, that question. Okay. So tonight we went over, and so now I know this. Okay? So now we've got that one, that one, that one, and we got that one for the sum law. So we can combine them. Okay? So for f of x equals x cubed minus 6x squared plus 5x minus 4, f prime of x is going to equal, right, I'm going to go 3x squared minus 6 times 2x to the first plus 5 minus 0. And do the 0. Which equals 3x squared minus 12x plus 5. So for any polynomial p of x, For any polynomial p of x, that's going to equal the derivative p of x. This is going to equal the derivative of, for any polynomial p, I'm going to take the derivative and I'm going to wind up with, right, this is c n x to the n plus c n minus 1 x to the n minus 1 plus dot 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 plus c1 x to the first plus c naught equals, and I'm going to wind up with cn times n minus 1 x to the n, I'm sorry, that should be an n. I'm going to wind up with cn x to the n minus 1 plus cn minus 1 times n minus 1 x to the n minus 2 plus dot 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 plus c1 x to the 0 plus 0. Okay. So how do we feel about that 1 to 5? You can't see because I'm on the wrong bloody screen again. So f of x equals x cubed minus 6x squared plus 5x minus 4. I take the derivative. I'm going to take this thing and stick it up front. I'm going to wind up with 3x squared minus 6 times 2, x to the first, plus 5, x to the 0, minus 0, which I simplify as 3x squared minus 12x plus 5. And then for any polynomial, remember polynomials have this ugly form. I'm going to take cn, is going to stay out front, n x to the n minus 1 plus blah, 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 plus a little 0 at the end. How do we feel about that, 1 to 5, now that you can see? I can see. Okay. So those are the basic derivative laws. So we actually covered a lot more than I thought we would. You can see these notes. If you go on to the notes section here, on the thing, you can actually find the notes here. I've got the stuff in green is just like extra, so don't worry about that stuff. This is about differentiability and continuity. The fact that one implies the other. Notice it's in purple. You have to know the fact, but the proof here, which is, I mean, it's there. There's a proof in there if you want to see it. Yes, so that's the H definition of the derivative. So all that's in there. If you really want to see all the binomial stuff, I love that stuff, the combinatorics, but that's just me. And there's the proof. Derivative of a constant function, multiple rule, the sum rule's in there, and then we just did that. Okay. Are there any questions for me? Okay. So, wow. Next time, so we've got these things. Next time, okay, we are going to, you can't see that because I'm haven't clicked on the screen again. Next time, we are going to do the following. We are going to do practice power rule. And then we are going to move on to the product rule. So this is going to be practicing power rule. This is going to be in class activity. And then we are going to move on to the power rule. Not the power rule, the product rule. All right. Any questions for me? All right. It's 8:15. Good luck on your test on Saturday. If you want to talk to me, remember extended office hours tomorrow. I will be happy to speak with you. I'm going to try to get the test review up as soon as possible. It's now 8:15, and I haven't finished writing the discrete math test yet. So I need to do that. And I will see everybody on Saturday morning. Office hours. Office hours tomorrow. I think I wrote them on the screen here. I think they're in the announcement. And the answer sheet is up. So go ahead and check out the answer sheet. And then the office hours on Friday, 2 to 5 tomorrow. You can't see that because I'm on the other screen. Okay, so the answer sheet is up. That was one of the announcements. And the office hours tomorrow from 2 p.m. to 5 p.m. Any other questions? Okay. Good evening.